Wearable sensors are becoming more common due to wireless technology that allows glucose concentrations, blood pressure, heart rate, and activity levels to be smoothly sent from sensor to smartphone for additional analysis. The majority of wireless sensors currently communicate using integrated Bluetooth chips, which are powered by tiny batteries. However, these traditional processors and power sources will most certainly be too large for next-generation sensors, which are becoming smaller, thinner, and more flexible. MIT researchers have developed a new type of wearable sensor that interacts wirelessly without the need for onboard processors or batteries. Their concept, which was published today in the journal Science, paves the way for chip-free wireless sensors. The sensor developed by the researchers is a type of electronic skin, or e-skin, which is a flexible, semiconducting material that adapts to the skin like electronic Scotch tape. The sensor's heart is an ultra-thin, high-quality film of gallium nitride, a material recognized for its piezoelectric capabilities, which means it can both emit an electrical signal and mechanically vibrate in response to an electrical impulse. The researchers discovered that they could employ gallium nitride's two-way piezoelectric characteristics for sensing and wireless transmission at the same time. The researchers created pure, single crystalline samples of gallium nitride, which they combined with a gold conducting layer to amplify any incoming or outgoing electrical signal. They demonstrated that the device was sensitive enough to vibrate in reaction to a person's heartbeat as well as the salt in their perspiration, and that the vibrations of the material produced an electrical signal that could be received by a nearby receiver. As a result, the gadget was able to wirelessly transmit sensing data without the use of a chip or battery. Chips demand a lot of power, but our technology might make a system very light without having any power-hungry chips, says Ji-Won Kim, an associate professor of mechanical engineering and materials science and engineering and a lead investigator at the Research Laboratory of Electronics. You could place it on your body like a bandage and remotely monitor your pulse, perspiration, and other biological signs by pairing it with a wireless reader on your iPhone. Ji-Won Kim's group earlier invented a process known as remote epitaxy, which they used to rapidly generate and peel away ultra-thin, high-quality semiconductors from graphene-coated wafers. Using this technology, they created and tested a variety of flexible, multifunctional electronic films. The engineers utilized the same process in their latest work to peel away ultra-thin single crystalline layers of gallium nitride, which is a very sensitive piezoelectric material in its pure, defect-free form. The researchers intended to employ a pure gallium nitride film as both a sensor and a wireless communicator of surface acoustic waves, which are basically vibrations across the films. These wave patterns can reveal a person's heart rate or, more delicately, the presence of particular substances on the skin, such as salt in perspiration. The researchers anticipated that a gallium nitride-based sensor attached to the skin would have its own intrinsic, resonant vibration or frequency, which the piezoelectric material would concurrently turn into an electrical signal, the frequency of which a wireless receiver could detect. Any change in the skin's circumstances, such as an increased heart rate, would alter the mechanical vibrations of the sensor as well as the electrical signal that it automatically communicates to the receiver. They put the new e-skin on participants' wrists and necks and used a simple antenna held nearby to wirelessly detect the device's frequency without physically touching the sensor. The gadget was capable of sensing and wirelessly transmitting variations in the surface acoustic waves of gallium nitride on the skin of volunteers that were connected to their heart rate. The gadget was also connected with a thin ion sensing membrane, which is a substance that selectively attracts a specific ion, in this instance sodium. With this modification, the gadget could detect and wirelessly communicate changing salt levels when a volunteer sweated while holding onto a heat pad. The researchers regard their findings as a first step toward chip-free wireless sensors, and they hope to link the present device with other selective membranes to monitor other key indicators. The researchers demonstrated sodium sensing, however, by changing the sensing membrane, you could detect any target biomarker, such as glucose or cortisol levels connected to stress. It is a very adaptive platform. Thank you for watching. If you like this video, don't forget to like, comment, share and subscribe.